So in this video, we're going to talk about how to dynamically allocate memory in C. Now, as a disclaimer, if you haven't watched our video on pointers or aren't generally familiar with the concept of pointers, you're probably going to want to go take a look at that before this. This video, dynamic memory allocation in general, works specifically with pointers, so you're going to want to make sure that you're comfortable with that before diving into this particular video. Without further ado, let's get started. Now, we've already seen how to work with pointers before, but typically we've only done it in the context of pointing a pointer variable that we declare statically at another variable that already exists. You may recall from our video on pointers, we had a line like int x equals 5, and then we would say int star px equals ampersand x. But that's the only way we've seen how to work with pointers, and that's static pointer usage, basically. In order to work with pointers statically as we have, we need to know exactly how much memory we're going to use at the moment we compile our program. So we're not going to be creating any memory on the fly. All the memory that we're going to use is already set up when we begin. That presents sort of an issue, right? What if we don't know how much memory we're going to have when we get started? Maybe you're going to be asking the user to give you a number, and they're going to generate 100 linked list objects. They're going to generate 100 of something, and you don't know that. Or maybe they generate 200 or 400. We wouldn't be able to predict this in advance. And so we need to use dynamic memory allocation in order to get new memory in our program while the program is already running. And that's a little bit different than anything we've seen before. We can do this by allocating memory from something called the heap. The heap is a giant pool of memory, and so far the only pool of memory that we're familiar with is called the stack. But dynamically allocated memory comes from the heap, and statically allocated memory, which is anything that you give a name to, typically like a variable name, is going to be set up on the stack, and anything that you create dynamically while your program is running is going to come from the heap. But as we can see from this diagram, the stack and the heap are actually the same big chunk of memory. It just so happens that the stack we allocate from the bottom to the top. Typically we visualize it. So the stack memory addresses will be a bit lower numbers, and the heap will have higher numbers and they'll allocate downward. So it's really one giant pool of memory, but we call it two different things depending on how it's being used. The stack for statically declared memory grows up, and the heap for dynamically allocated memory grows down. How do we get at this dynamically allocated memory? How do we access memory on the heap? We need to use a new function called malloc. You can get malloc by including standardlib.h, stdlib.h, and the only argument that you need to pass to malloc is how many bytes of memory that you want. So if you want an integer, you say malloc 4. If you want a character, you malloc 1. If you want a double, you malloc 8, and so on. And you can be more complex than that, as we'll soon see. What malloc will then try and do is find some chunk of memory the size that you asked for on the heap. So it'll go and try and find 8 contiguous bytes of memory. For example, if we're allocating a double, it will go and try and find 8 contiguous bytes of memory from the heap. And what it will do is it will return to you a pointer to that memory, right? So the only way we're going to be able to access dynamically allocated memory or use it is by dereferencing the pointer that we get back from malloc. And that's why it's important to understand pointers before going forward. Now, it's possible that malloc might not actually be able to give you back memory, in which case it's going to return to you null. And so one of the first rules to remember about dynamically allocated memory is to always check for null after malloc. Now, why might this happen? Maybe you've run out of memory, the stack and the heap have just completely run out, or there's been some sort of catastrophic failure that we can't predict. But either way, if you recall from our pointers video, dereferencing a null pointer, bad news. So the first thing you want to do after you malloc, of course, is to check to make sure that you didn't get back null. And if you did, you're going to need to abort your program because something has gone wrong and you can't proceed with what you currently have. So if we want to just get an integer, statically declare it, we can just say int x. That's going to create a variable called x on the stack that we can then assign any value that we like to. If you want to dynamically allocate an integer, we say the following: int star px equals malloc 4. And the reason we say 4 here is because there are 4 bytes in an integer. I easily also could have used the size of operator, which is available in C. Basically, you pass it a type. So it's a little bit different. Usually with functions, you pass in a variable. With malloc, you pass in, or with size of rather, you pass in a type, and it will return how many bytes that type takes up on the system. So int star px equals malloc size of int, or int star px equals malloc 4, basically means malloc is going to go try and find you 4 bytes of memory that are next to each other on the heap, and they will malloc will return to you a pointer to that memory called px. And then we could dereference that pointer, as we've seen in the pointers video, to manipulate it, to put a value in there, to do whatever we want to do with it. Let's see another example of this. Maybe we want to get an integer from the user. So recall that in CS50 we have the getInt function that we can use. int x equals get int. We're basically prompting the user for some integer value, and they'll give us some number, hopefully, in this example, a positive number. Let's say I want to declare an array of that many floats on the stack. I can do this by saying float stack array, and then in square brackets, which again indicates the size of the array, x. This is legal in C99 and C11. If you're using a very old version of C, this was actually previously not allowed, but you can do this. We can basically get a variable sized array on the stack, which we're doing here because we don't know how big it's going to be in advance. We're just getting it from the user. But this is how we would declare an array of floats on the stack, where the number of items in that array is the number the user just gave us. And I can also dynamically allocate an array of floats on the heap, not on the stack, remember, because we're dynamically allocating the memory this time. Float star heap array, so that's my pointer to the memory that I'm getting. And I want to malloc x times the size of a float. So if I want to have 50 floats, I need 50 times the size of a float. So 50 times 4. Maybe I want 100, so it'd be 100 times 4. So that's why we're doing the multiplication there. And that's going to, malloc is going to return to us one giant block of memory that size, which we can then just treat like any other array. There's one catch with dynamically allocated memory, though, that we have to deal with, and that's something that we haven't seen before, and that is that it is not released back to the system when you are done. So if you haven't yet seen our video on the call stack or stack frames, this might not be something you're aware of yet, but typically when a function finishes running, what happens is all of the memory that was created for purposes of that function's existence gets destroyed, and it is released back to the system to be used somewhere else. So another function call that might come up can use that same bit of memory before. That's kind of convenient, right? This system is constantly recycling where it can. But when you tell the system, I want a block of memory, the system is not going to assume anything about it. It's not going to assume that, you know, it hasn't seen you make a call with it for 50 lines or whatever, and it's just going to dynamically free it or release it back to the system. And if you fail to release enough memory back to the system, what you get is something called a memory leak. And memory leaks are really not good because they can really slow down your system. And in fact, there are some browsers that shall remain nameless that are sort of notorious for not freeing memory or not releasing memory back to the system when it's done. And that can really cause your computer to slow down because that browser is basically hogging a bunch of memory, and the other programs on your computer can't use it because the browser has sort of allocated it and said, no, this is mine, I need it, but it never releases it back to be shared by the other things on the system. So that's why if you leave a browser open for like days, or some browsers open for days or weeks, you might notice your computer starts to slow down. Now the rule is, as I mentioned before, when you're done working with dynamically allocated memory, all you have to do is free it. And free is another function that is available in standard lib.h. And basically what you pass to free is a pointer to any memory that you have dynamically allocated previously. And basically that's just telling the system, I'm done, you can use this memory for whatever you'd like. So here's another example. Let's say we want to malloc a 50 character long array. So basically a big string, we're going to call it word. We dynamically allocate it. Then we just do some stuff with it. Maybe we're in the middle of a function. We're changing its value, we're assigning new characters, we're printing it out, for example, and then we decide that we're done with it. How do we release this back to the system? We just need to free it. So we free word. Word is the pointer to that block of memory. That's the thing that we want to free. So there are three basic rules for malloc and free that are really important to internalize. The first is that everything that you malloc has to be freed before your program finishes running. Now granted, if your program actually finishes running, once it's completely done, once you've returned 0 from main, for example, then it will be freed. But it's a good practice to make sure that everything that you allocate, you specifically free by explicitly calling the free function, as opposed to just relying on the system to do it once your program is completely done. So everything that you malloc, you have to free. Rule number 2, only things that you malloc are things that you should free. So if you statically declared a variable, you don't want to free it. The system is going to take care of releasing all statically declared memory for you. It's only dynamically allocated memory, only memory that you malloc are things that you should free. And then make sure not to free the same block of memory more than once, because that can create a problem of a double free, and you have sort of an inverse memory leak, like a memory flow or something, where you trick the system into thinking that you have more memory than you do. It's not the kind of thing that you actually want to do. So remember, everything you malloc, you should free. Only things that you malloc, you should free. And don't free anything more than once. Let's just close this video by taking a look at a couple of lines of code and a visual example to show you exactly what's happening as we do it. So first, let's statically declare an integer called m. And so this would look something like this. I've colored the box green because in my head, sort of integers are always in green boxes, and I've written the label M on the box. Then I'm going to say int star A. So here I'm statically declaring a pointer called A. So recall that I like to think of it's an int star, so it's int like, so it'll be green. It's a greenish box. It's not a green box because that's for ints, but int stars are sort of greenish. They refer to ints. So this is another box, and this one is called A. Then I can say int star B equals malloc size of int. So what's going to happen here? Well, I'm going to have something called B that I'm giving a name to, so that's going to be sort of a light greenish box, and I'm asking malloc to dynamically give me 1 int's worth of space. And so what actually happens sort of visually is this. Notice that the actual integer, I didn't give a name to. I don't have a name for it. That's how it's one way, typically, that I know I don't have a statically declared integer. The only way that I can refer to that green box is by dereferencing the pointer called B. So B has a name, that's statically declared, but I dereference B in order to get to this dynamically allocated memory. And of course, I'm not going to do this here, but the first thing I should do immediately after this is check to make sure that B is not null. If B is null, something has gone wrong. I need to stop my program immediately. Next, I can say something like this, A equals ampersand M. If you recall from our video on pointers, basically this just means A points to M, so that just creates this arrow here. Next up, let's say A equals B. Before I show you what's going to happen here, can you try and guess a little bit about what it's going to be? Take a look at the diagram, think about how relationships might change. If I say A equals B, what am I saying? What I'm saying is that A and B are now going to point to the same location. In particular, A is going to point where B currently points. And so instead of pointing to M, A is now going to point over here to this dynamically allocated block that I can currently only reference. Now I can reference it multiple ways. Now I could say star A or star B. I can reference it either way because both of those same statically declared variables point to the same location. I can then say M equals 10. That's not a problem because 10 was statically declared. It's a box that I know about already. It's got a name. So when I say M equals 10, I'm just saying put 10 into this green box called M. Star B equals M plus 2. It's a little weird, right? But what's M plus 2? Well, M is 10, so 10 plus 2 is 12. And star B equals 12. When I say star B, I'm dereferencing B, so I'm going to travel along the arrow to where B points, and I'm going to put 12 in that location, okay? Next up, I'm going to free B. So remember what happens with free is we are telling the system we're no longer working with this, we're done. You can take these 4 bytes back or whatever the size of this is. This one happens to be 4 bytes. You can take it back and use it for whatever you want in some other program. So when I free B, this memory basically goes away. A and B still point to where it used to be, but I no longer have access to it. If I try and touch it, the system might get upset with me. So for example, if I try and say this, star A equals 11, what's going to happen? Unpredictable behavior, right? We don't know. We might get a segmentation fault because we're touching memory that we're no longer, we don't have write privileges to anymore. You might get away with it, depends on where that memory happened to live on the system, but it's unpredictable. So once you free memory, remember, you're telling the system, I don't need it anymore. So if you then try and use it, some strange things might result. Dynamic memory allocation is a little strange to get used to because we're so used to this idea of creating a variable and assigning it a value and just manipulating it in that way that using pointers to sort of control where memory is and change it indirectly through pointers can be a bit strange, but just keep practicing with it. Internalize those rules about how to malloc and free successfully to make sure that you don't create memory leaks or anything like that, and you should be off to a good start. I'm Doug Lloyd. This is CS50. video on recursion, the process might have seemed a little bit magical, right? Like, how does a function know to wait for another function and pass its data to some other thing that's running at the same time? It can seem a little magical at the outset if you don't understand exactly how functions are called and operate in C. And the way they operate is using something called the call stack. And the way the call stack works is as follows. If you call a function, basically what happens is a big chunk of memory is set aside somewhere on the system for that function to do its work. So for example, if you call a function and the first thing you do is declare a couple of variables, what's going to happen is a stack frame or a function frame will be created, a big chunk of memory, and those variables will be given space. So if it's 3 integers, you'll get 3 4-byte chunks, just like the size of an integer, as well as some space to do some calculations and whatever else the function might need. And that's where the function will do all of its work. Now, it's possible that more than one function's frame might exist in memory at any given time. So for example, let's say the function main calls another function called move, and then the function move calls another function called direction. At that point, all 3 of those functions have open frames, but in general, only one of those frames will ever be active. Only one of those functions is ever running at a given time, even though all 3 of them have space set aside and are sort of like hanging out waiting to do something. Now, the way these frames are arranged is in what's called a stack, and the frame for the most recently called function is always the one at the top of the stack, and that is called the active frame. So again, if main called move and move called direction, you can think about this like a stack as follows, where main is at the bottom, called move and move called direction, you can think about this like a stack frame. So again, if main called move and move called direction, you can think about this like a stack as follows, where main is at the bottom, move is above it, direction is on the top, and direction is the active frame. That is the only function that is doing anything at the moment, whereas move and main are just sort of like waiting to become the active frame. They're waiting to become the frame that is at the top of the stack. When you call a new function, a new frame is what's called pushed onto the top of the stack. So if you call a new function, that function immediately gets space in memory and is put on top of the call stack, and it becomes the active frame. And whatever was the active frame, if there was one, is kind of on pause. It's just sitting there kind of like it's in a holding pattern, waiting to become the active frame again. When a function finishes its work, such as by returning most commonly, or perhaps reaching the end of the line if it's a void function, it doesn't have a return value, that frame is what's called popped off of the stack. And then the frame that was in second place, since this frame is now gone, that becomes the active frame. It resumes where it left off. If you would hit pause on that function, it's going to pick up immediately where it left off. This is actually why recursion works, because all of these frames are running, but only one of them is moving at a given time. The rest of them are all running, but they're on pause. They're just waiting to become the new top of the stack again. If we call another function, that function, the active frame goes on pause again, the function that was just called is put on top, and so on, until all of the function frames are finished. So let's take a look at a visualization of this and an example using the factorial function to see if we can help make this a little bit clearer. So this is the entirety of a factorial file, for example. And inside of that factorial file, I have two functions, fact, which is going to be a recursive implementation of factorial, and main, which basically just call or prints out the value of factorial, in this case, of 5. So we start at the beginning of main, and the first thing main does is it calls another function. It calls printf. As soon as it does that, main kind of is on pause. It's kind of hanging out right here, and it is waiting for printf to do its work. Well, what does printf have to do? It just has to print out a number, but it has to print out factorial of 5, but it doesn't know factorial of 5. It has to make a function call. So printf then goes on pause and waits for factorial of 5, which now becomes the new active frame. So in the factorial of 5 frame, what's happening? Well, we're passing in the value 5 to the fact function, and then it's going to check, well, is n equal to 1? No. So then it's going to return n times fact n minus 1. Okay, so now the factorial 5 frame is basically calling a new function, passing in another call to factorial, passing in 4 as the parameter instead. So the factorial of 5 frame now goes on pause, and a frame for factorial of 4 becomes the new active frame. And it's going to go through the same process. Is 4 equal to 1? No. So instead it's going to return n times, in this case, or 4 times factorial of 3, another function call. So factorial 4 frame goes on pause, factorial of 3's frame becomes the new active frame, and we repeat this process again for factorial of 3, for factorial of 2, and then we get to factorial of 1. So at the very beginning, right when factorial of 1 is called, there are 7 function frames in the call stack. Factorial of 2, 3, 4, 5, printf, and main are all on pause at the lines that you see there. They're just kind of hanging out, waiting to become the new active frame again. But they're not moving from those arrowed indicators. So factorial of 1's frame begins. It asks the question, is n equal to 1? Well, in this case, the answer is yes. It's going to return 1. Now remember what happens when a function returns a value. That frame is done. It goes away, and that means that it gets popped back off of the call stack, and then the frame that is below it will become the new active frame. So factorial of 1 returns a 1. At this point, its frame is destroyed, and factorial of 2 can now get unpaused. Now factorial of 2 is that dark blue line on the left there, and it was waiting on the return value of factorial of 1. Well, factorial of 1 said, I returned a 1 to you, so factorial of 2 is going to return 2 times 1, or 2. It is now also returning, and so when it returns, it gets popped off the stack, its function frame is destroyed, and factorial of 3 becomes the new active frame. Factorial of 3 was waiting on factorial of 2, which returned a 2. So it's going to return 3 times 2, or 6. It returns a value, its function frame is popped off of the stack, it is destroyed. Factorial of 4 becomes the new active frame. Factorial of 4 was waiting on factorial of 3. It got its answer back of 6, so it's going to return 4 times 6, or 24. And it's going to return that value to factorial of 5, which has been waiting for factorial of 4 to finish its work. It returns 5 times 24, which is 120. When that frame is destroyed, now we resume at printf. Printf has that dark red line on the bottom there. It was waiting on factorial of 5, which just returned a 120. So what printf does is it prints out 120, and then its job is done. It doesn't have anything else to do. It's not waiting on another function call. And so it finishes executing. It doesn't return anything, but it reaches the last. It doesn't have anything else to do. So its function frame is destroyed. It gets popped off of the stack. And then all we have to do is see where main left off. Well, that was all main had. And so main's function frame will then pop off the stack as well. And this program will have completed its job by printing out 120. Hopefully that illustration of the call stack helped to show exactly how recursion works and how these functions, hopefully that as well, and this program will have completed to show exactly how recursion works and how these functions are waiting and interacting with each other to allow the recursive process to occur. I'm Doug Lloyd, this is CS50. taking the frame is destroyed. Now we resume at printf. Printf is terminal window, but if you clear your screen, there's really no evidence that it existed. We don't have a means of storing persistent information that exists after our program has stopped running, or we haven't up to this point. Fortunately, though, C does provide us with the ability to do this by implementing something called a file, a structure that basically represents a file like any that you would double-click on your computer if you're used to a graphical user environment. Generally, when we're working with C, we're actually going to be working with pointers to files, file stars, but except for a little bit when we talk about a couple of the functions that work with file pointers, you don't need to have really dug too deep into understanding pointers themselves. There's a little teeny bit where we will talk about them, but generally file pointers and pointers, while interrelated, are not exactly the same thing. Now, what do I mean when I say persistent data? What is persistent data? Why do we care about it? Say, for example, that you're running a program or you've written a program that's a game, and you want to keep track of all of the user's moves so that maybe if something goes wrong, you can review the file after the game. That's what we mean when we talk about persistent data. In the course of running your program, a file is created, and when your program has stopped running, that file still exists on your system. And we can look at it and examine it. And so that program would be said to have created some persistent data that exists after the program has finished running. Now, all of these functions that work with creating files and working and manipulating them in various ways live in standard.io.h, which is a header file that you've likely been including at the top of pretty much all of your programs because it contains one of the most useful functions for us, printf, that also lives in standard.io.h. So you don't need to include any additional files probably in order to work with file pointers. Now, every single file pointer function, or every single I/O function, file I/O, input-output function, accepts as one of its parameters or inputs a file pointer, except for one, fopen, which is what you use to get a file pointer in the first place. But after you've opened a file and you get file pointers, you can then pass them as arguments to the various functions we're going to talk about today, as well as many others, so that you can work with files. So there are 6 pretty common basic ones that we're going to talk about today. fopen and its companion function fclose, fgetc and its companion function fputc, and fread and its companion function fwrite. All right, so let's get right into it. Fopen. What does it do? Well, it opens a file and it gives you a file pointer to it. So then you can then use that file pointer as an argument to any of the other file I/O functions. The most important thing to remember with fopen is that after you have opened the file or made a call like the one here, you need to check to make sure that the pointer that you got back is not equal to null. If you haven't watched the video on pointers, this might not make sense, but if you try and dereference a null pointer recall, your program will probably suffer a segmentation fault. So we want to make sure that we got a legitimate pointer back. The vast majority of the time, we will have gotten a legitimate pointer back. It won't be a problem. So how do we make a call to fopen? It looks pretty much like this. File star PTR, PTR being a generic name for a file pointer, fopen, and then we pass in 2 things, a file name and an operation we want to undertake. So we might have a call that looks like this. File star PTR1 equals fopen file1.txt, and the operation I've chosen is R. So what do you think R is here? What are the kinds of things we might be able to do to files? So R is the operation that we choose when we want to read a file. So we would basically, when we make a call like this, be getting ourselves a file pointer such that we could then read information from file1.txt. Similarly, we could open file2.txt for writing, and so we can pass PTR2, the file pointer I've created here, as an argument to any function that writes information to a file. And similar to writing, there's also the option to append a. The difference between writing and appending being that when you write to a file, if you make a call to fopen for writing, and that file already exists, it's going to overwrite the entire file. It's going to start at the very beginning, deleting all of the information that's already there. Whereas if you open it for appending, it will go to the end of the file if there's already text in it or information in it, and it will then start writing from there. So you won't lose any of the information you've done before. Whether you want to write or append sort of depends on the situation, but you'll probably know what the right operation is when the time comes. So that's fopen. What about fclose? Well, pretty simply, fclose just accepts a file pointer, and as you might expect, it closes that file. And once we've closed a file, we can't perform any more file I/O functions, reading or writing, on that file. We'd have to reopen the file another time in order to continue working with it using the I/O function. So fclose means we're done working with this file, and all we need to pass in is the name of a file pointer. So on a couple slides ago, we fopened file1.txt for reading, and we assigned that file pointer to PTR1. Now we've decided we're done reading from that file. We don't need to do any more with it. We can just fclose PTR1, and similarly could we fclose the other ones. All right, so that's opening and closing. Those are the 2 basic starting operations. Now we want to actually do some interesting stuff, and the first function that we'll see that will do that is fgetc, file get a character. That's what fgetc generally would translate to. Its goal in life is to read the next character, or if this is your very first call to fgetc for a particular file, the first character, but then after that you would get the next one, the very next character of that file, and stores it in a character variable, as we've done here. Char ch equals fgetc, pass in the name of a file pointer. Again, it's very important here to remember that in order to have this operation succeed, the file pointer itself must have been opened for reading. We can't read character from a file pointer that we opened for writing. So that's one of the limitations of fopen, right? We have to restrict ourselves to only performing one operation with one file pointer. If we wanted to read and write from the same file, we would have to open 2 separate file pointers to the same file, one for reading, one for writing. So again, the only reason I bring that up now is because if we're going to make a call to fgetc, that file pointer must have been opened for reading. And then pretty simply, all we need to do is pass in the name of the file pointer. So char.ch equals fgetc ptr1. That's going to get us the next character, or again, if this is the first time we've made this call, the first character of whatever file is pointed to by ptr1. Recall that that was file1.txt. It'll get the first character of that and we'll store it in the variable ch. Pretty straightforward. So we've only looked at 3 functions and already we can do something pretty neat. So if we take this ability of getting a character and we loop it, so we continue to get characters from a file over and over and over, now we can read every single character of a file. And if we print every character immediately after we read it, we have now read from a file and printed its contents to the screen. We've effectively concatenated that file on the screen, and that's what the Linux command cat does. If you type cat and then a file name, it will print out the entire contents of the file in your terminal window. And so this little loop here, it's only 3 lines of code, but it effectively duplicates the Linux command cat. So this syntax might look a little weird, but here's what's happening here. While ch equals fgetc ptr is not equal to eof. That's a whole mouthful, but let's break it down just so it's clear on the syntax. Because I've consolidated it for the sake of space, although it's a little syntactically tricky. So this part in green right now, what is it doing? Well, that's just our fgetc call, right? We've seen that before. It's obtaining one character from the file. Then we compare that character against EOF. EOF is a special value that's defined in standardio.h, which is the end of file character. So basically what's going to happen is this loop will read a character, compare it to EOF, the end of file character. If they don't match, so we haven't reached the end of the file, we'll print that character out. Then we'll go back to the beginning of the loop again. We'll get a character, check against EOF, print it out, and so on and so on and so on, looping through in that way until we've reached the end of the file. And then by that point, we will have printed out the entire contents of the file. So again, we've only seen fopen, fclose, and fgetc, and already we can duplicate a Linux terminal command. All right, so as I said at the beginning, we had fgetc and fputc, and fputc was the companion function of fgetc, and so as you might imagine, it is the writing equivalent. It allows us to write a single character to a file. Again, the caveat being, just like it was with fgetc, the file that we're writing to must have been opened for writing or for appending. If we try and use fputc on a file that we've opened for reading, we're going to suffer a bit of a mistake. But the call is pretty simple. fputc capital A ptr2, all that's going to do is it's going to write the letter A into file2.txt, which was the name of the file that we opened and assigned the pointer to ptr2. So we're going to write a capital A to file2.txt, or we'll write an exclamation point to file3.txt, which was pointed to by ptr3. So again, pretty straightforward here. But now we can do another thing. We had this example we were just going over about being able to replicate the cat Linux command, the one that prints out to the screen. Well, now that we have the ability to read characters from files and write characters to files, why don't we just substitute that call to printf with a call to fputc, and now we've duplicated cp, a very basic Linux command that we talked about way long ago in the Linux commands video. We've effectively duplicated that right here. We're reading a character, and then we're writing that character to another file. Reading from one file, writing to another, over and over and over, again until we hit EOF. We've got to the end of the file we're trying to copy from, and by that point we'll have written all of the characters we need to the file that we're writing to. So this is CP, the Linux copy command. Okay, so at the very beginning of this video, I had the caveat that we would talk a little bit about pointers. Here is specifically where we're going to talk about pointers in addition to file pointers. So this function looks kind of scary, right? It's got several parameters. There's a lot going on here. There's a lot of different colors and text. But really, it's just the generic version of fgetc that allows us to get any amount of information. It can be a bit inefficient, right? If we're getting characters one at a time, iterating through the file one character at a time, wouldn't it be nicer to get 100 at a time or 500 at a time? Well, fread and its companion function fwrite, which we'll talk about in a second, allow us to do just that. We can read an arbitrary amount of information from a file, and we store it somewhere temporarily. Instead of being able to just fit it in a single variable, we might need to store it in an array. And so we pass in 4 arguments to fread. A pointer to the location where we're going to store information, how large each unit of information will be, how many units of information we want to acquire, and from which file we want to get them. Probably best illustrated with an example here. So let's say that we declare an array of 10 integers. We've just declared it on the stack arbitrarily, int r10. So that's pretty straightforward. Now what we're doing, though, is the fread call is we're reading size of int times 10 bytes of information. Size of int being 4, that's the size of an integer in C. So what we're doing is we're reading 40 bytes worth of information from the file pointed to by PTR, and we're storing those 40 bytes somewhere where we have set aside 40 bytes worth of memory. Fortunately, we've already done that by declaring ARR, that array right there. That is capable of holding 10 4-byte units, so in total it can hold 40 bytes worth of information, and we are now reading 40 bytes of information from the file, and we're storing it in ARR. Recall from the video on pointers that the name of an array, such as ARR, is really just a pointer to its first element. So when we pass in ARR there, we are in fact passing in a pointer. Similarly, we can do this. We don't necessarily need to collect our, we don't need to save our buffer on the stack. We could also dynamically allocate a buffer like this using malloc. Remember, when we dynamically allocate memory, we're saving it on the heap, not the stack. But it's still a buffer. It still is, in this case, is holding 640 bytes of information because a double takes up 8 bytes, and we're asking for 80 of them. We want to have space to hold 80 doubles. So 80 times 8 is 640 bytes of information, and that call to fread is collecting 640 bytes of information from the file pointed to by PTR and storing it now in ARR2. Now we can also treat fread just like a call to fgetC. In this case, we're just trying to get one character from the file. And we don't need an array to hold a character. We can just store it in a character variable. The catch, though, is that when we just have a variable, we need to pass in the address of that variable, because recall that the first argument to fread is a pointer to the location in memory where we want to store the information. Again, the name of an array is a pointer, so we don't need to do ampersand array, but C, the character C here, is not an array, it's just a variable. And so we need to pass in ampersand C to indicate that that's the address where we want to store this 1 byte of information, this 1 character that we're collecting from PTR. fwrite, I'll go through this a little more quickly, is pretty much the exact equivalent of fread, except it's for writing instead of reading. Just like the other, we've had open and close, get a character, write a character. Now it's get arbitrary amount of information, write arbitrary amount of information. So just like before, we can have an array of 10 integers where we already have information stored, perhaps. So there's probably some lines of code that should go between these two, where I fill ARR with something meaningful. I fill it with 10 different integers. And instead, what I'm doing is writing from ARR. I'm collecting the information from ARR, and I'm taking that information and putting it into the file. So instead of it being from the file to the buffer, we're now going from the buffer to the file. So it's just the reverse. So again, just like before, we can also have a heap chunk of memory that we've dynamically allocated and read from that and write that to the file. And we can also have a single variable capable of holding 1 byte of information, such as a character. But again, we need to pass in the address of that variable when we want to read from it, so we can write the information we find at that address to the file pointer PTR. There's lots of other great file I/O functions that do various things besides the ones we've talked about today. A couple of the ones you might find useful are fgetS and fputS, which are the equivalent of fgetC and fputC, but for reading a single string from a file. Instead of a single character, it'll read an entire string. fprintf, which basically allows you to use printf to write to files. So just like you can do the variable substitution using the placeholders %i and %d and so on with printf, you can similarly take the printf string and print something like that to a file. fseek, if you have a DVD player, is the analogy I usually use here, is sort of like using your rewind and fast forward buttons to move around the movie. Similarly, you can move around the file. Is one of the things inside that file structure that C creates for you is an indicator of where you are in the file. You're at the very beginning at byte 0. Are you at byte 100, byte 1000, and so on? You can use fseek to arbitrarily move that indicator forward or backward. And ftell, again, similar to a DVD player, is like a little clock that tells you how many minutes and seconds you are into a particular movie. Similarly, ftell tells you how many bytes you are into the file. feof is a different version of detecting whether you've reached the end of the file. And ferror is a function that you can use to detect whether something has gone wrong working with a file. Again, this is just scratching the surface. There's still plenty more of file I/O functions in standardio.h, but this will probably get you started working with file pointers. I'm Doug Lloyd. This is CS50.
In this lab, your task is going to be to write a program in C that changes the volume of an audio file. Specifically, in this lab, we're going to be working with WAV files, a standard file format for representing audio information. What is the structure of a WAV file? Well, like any file, these files consist of bytes, and in particular, in a WAV file, the first 44 bytes of that file are the header for that WAV file that contain information about that file that your computer or programs on your computer might need to know in order to read and understand and interpret that file. After the 44-byte header are 2-byte samples of audio. Many of these 2-byte samples of audio repeated back to back to back, where each of these 2-byte samples represents the value of some audio waveform at a particular point in time. So ultimately, your WAV file is going to consist of one 44-byte header, followed by many of those 2-byte samples. And the interesting thing about those 2-byte samples is that each one is really just a number, and if you want to change the volume of a sample, you're going to multiply that sample by a number. If I have an audio sample and I want to double the volume, for example, I would take each of the samples of audio in the audio file that I'm trying to modify and just multiply each of those sample values by 2. Likewise, if I'm trying to cut the volume in half for a particular audio file, then I'll take each of the 2-byte samples and I'll multiply each by 0.5, or 1/2, in order to cut the volume in half as well. Ultimately, the way your program is going to work is we're going to run our program as /volume followed by 3 command line arguments. The first command line argument is an input WAV file, some file that already exists representing the audio file that we're here going to try to modify. The next command line argument is the name of some output file, some new audio file that our program is going to generate that is going to have the modified volume. And finally, the last command line argument to this program is going to be a floating point number representing the factor by which to change the volume of the original audio file. In this case, for example, we're using a factor of 2.0 to mean we want to double the volume of the audio file. But if instead we had tried to use 0.5, for example, as the factor, then we would be cutting the volume of the audio file in half. So here's what you're going to need to do in this lab. In order to take the input file and then generate a new output file that's the same audio, but just with the volume changed, you're going to want to start with the header of that WAV file, since the header, those first 44 bytes of the file, are the first thing you'll find inside the input WAV file. So you'll initially want to read the header from the input file, and then you'll want to write that exact same header to the output file. After the header, recall, comes each of those 2-byte samples, many 2-byte samples back to back in the file, representing the audio waveform of the file itself. So you'll want to repeat, for each of those 2-byte samples, you'll want to first read the sample from the input file, likely into some sort of variable, and then you'll want to multiply that sample value by the volume factor. If you're trying to double the volume of the sample, then you'll double that value. If you're trying to triple it, you'll multiply it by 3. If you're trying to cut the volume in half, you'll multiply by 0.5, for example. And after you've done that multiplication, you'll then write that new sample to the output file, so that the updated sample with the modified volume ends up being written to the output file for each of the samples of audio in that entire file. As you go about working on this lab, a couple of techniques will be helpful. One is taking advantage of the various different types that C gives you for dealing with data of different sizes. uint8t, for example, is a type that stores unsigned integers that are 8 bits or 1 byte large. And this is useful anytime you want to represent just a generic byte of data. For example, if you're trying to read in a header that has 44 bytes of data, you might use an array of 44 of these unsigned integers of 8-bit size as uint8t's inside of an array to store your header. Meanwhile, int16t is a type that stores signed integers, meaning they could be positive or 0 or negative, of 16 bits or 2 bytes each. And ultimately, this is a great choice of type for representing your samples, because we know that each sample is 2 bytes large, and int16t is the perfect size for representing this kind of information. Next, you're also going to want to deal with reading and writing files. And for that, these two functions will likely prove helpful, fread and frwrite. Fread will read a certain number of bytes from some file into memory inside of your computer, and likewise, frwrite can write data from your computer's memory to a particular file. And you'll likely want to look to the documentation for each of these functions, fread and frwrite, to get an understanding for what arguments they take in what order, and how you might use these functions to read from the input file and then write your updated data to your output file. Now, let's take a look at the distribution code that we give to you as part of this lab. You'll notice that one of the first things we give you is a constant integer called header size equal to 44. You can use this variable anytime you need to reference the number of bytes inside of the header of a WAV file as this constant integer called header size. Inside of the main function, we've already done some work for you, first checking the number of command line arguments to ensure that when the user is running this program, they're providing an input file, an output file, as well as some factor by which to change the volume of the input file. We then open the input file, checking to make sure that the input file was able to be opened correctly. We then open the output file using the W mode, W for writing that file, in order to make sure that we can open the file that we're going to be writing to correctly. And then we compute the factor, converting that factor to a floating point number, like 2.0 for doubling the volume, or 0.5 for cutting the volume in half. Here then are your to-dos. The first thing you'll want to do is to copy the header from the input file to the output file. Recall that you know that header is always going to be 44 bytes, so you'll likely want to use fread to read 44 bytes from your file, and then frwrite to write 44 new bytes to the output file. Then you'll want to go through each of the samples, likely using some kind of loop to loop through the input file until you get to the end of the file, and for each of those 2-byte samples, to read it into memory, update the volume, and then write that updated sample to the output file as well. You'll notice that we provide you with a sample input file, input.wav, which you can listen to as just a sample of audio, and you can run your volume program on this file, passing in a factor of 2.0 to double the volume, or some other factor to change the volume by a different amount, and then you should be able to listen to that new output file and detect that it does in fact have the same audio, just with a different volume. After you've done all of those steps, you should then have a program that can take any WAV file and change the volume by a particular factor. My name is Brian, and this was Volume. Let's take a look at how you might have solved the volume problem.
Sample.
decreasing the volume of the audio file. So let's now take a look at the solution inside of volume.c. We gave you some of the initial code inside of the main function already, but the first thing you needed to do was to deal with the header, to be able to read the header from the input file and to write that header to the output file. The first thing you might have needed to do was to create some place in your computer's memory into which to read that header. And so the first thing we have here is the declaration into which to read, called header. Its type is uint8t, a type for unsigned 8-bit integers, just representing bytes. And how many bytes do we want in the header? Well, we want header size bytes. Recall that header size is a constant integer, just equal to 44. That's the number of bytes in the header of a WAV file. So we could have written header 44 here, but it's slightly better designed to take advantage of this constant rather than reuse the number over and over by just saying header size. So we now have this buffer, as we might call it, to represent the header. And now we need to read that buffer from the input file. And so here we're reading header size bytes from the input file, and we're going to go ahead and read it into the header variable that we've created here. And after we've read it into memory, then we can write that same data to the output file, calling the fwrite function and then writing the contents of that header to the output file. And how many bytes are we going to write? Well, we're going to write header size bytes. Those lines are going to have the effect of reading 44 bytes from the input file and then copying them into the first 44 bytes of the output file. Next, after the header of an input file, is going to come all of the bytes of data, the sample bytes that are contained within the audio file as well. And for each of those 2-byte samples, we want to read that sample into memory, modify it to adjust its volume, and then write it to the updated file. So here, we're going to start by creating another buffer. This time the buffer doesn't need to store 44 bytes of data, it just needs to store enough data for a 2-byte sample. And for that, we can use the int16t type for a type that stores an integer with 16 bits. And now, we're going to repeat this inside of a loop. We're going to use the fread function to read from the input file into the buffer, passing in the address of the buffer so that fread knows where to put the memory that it's reading. And we're going to read one sample of 16 bits, in other words, 2 bytes. And because this is in a loop, the effect this loop is going to have is it's going to repeatedly read a sample, one sample after another, until we reach the end of the file. Fread returns to us the number of blocks of data it was able to read successfully. And so once it's no longer able to read any more data from the file, fread will return 0. And at that point, while is going to treat that as false and will exit the loop. So now we've read the sample into memory as this variable buffer. And now we need to update the buffer by multiplying it by factor. If factor is 2, that has the effect of doubling the volume. If factor is less than 1, it has the effect of decreasing the volume. So factor could be some other floating point number to change the value of this particular sample. And once we've changed the value of the sample, now we just need to write that updated data to the output file. Again, using fwrite to do so, writing data from the buffer to the output file. And how much data are we writing? Well, it's however big an int16t is, which in this case is going to be 2 bytes. After that, we wrote the code to close the files for you already. So now when you run this program, you should be able to specify an input audio file, specify a new file name for an output audio file, as well as a factor by which to change that volume. And you should be able to generate new audio files that have the same audio, but just with a different volume compared to the original. My name is Brian, and this was Volume.
you